Hello, everybody. Thank you to be present. Today we want to show you the sustainable robotic manufacturing of lightweight material structures, which we developed in GRADEL. We will start. Mainly, we are here with 3 partners. The project was made GRADEL itself, and then we have Thales Alenia Space, one of our customers, and LIST, which helps us also to calibrate the material and the impregnation system qualification for space applications. Mainly, I am David MACIEIRA. Here we have Gilles POMMATAU, and Henri Perrin unfortunately could not be present. We will start then the presentation. GRADEL taught why lightweight structures. We will divide it by lightweight structures. Then we will present a space case study, lightweight challenges in satellites. Then we will show you what is GRAM, which is GRADEL Robotic Additive Manufacturing Solutions. We will show you also homogeneous and repeatable thermomechanical properties, which we calibrated with LIST. Then at the end, you will have a space demonstrator development, how it works and why it's so important. And then let's go. Okay, why lightweight structures? Lightweight structures, in our opinion, we have a big consumption in the Earth about natural resources. And if we make our structures lightweight and we make additive manufacturing, we can reduce our footprint, we can reduce our use of material, resource, and we make everything more efficient. And we think this is the solution also to go to reduce our resources. We'll let my colleague.
You hear me?
Yes.
So I just will speak to you about the specification of space requirement, because the objective is to qualify this kind of part for space. So just a small word about my company, Thales Alenia Space, which is a main provider of satellite system from ground to low Earth orbit to geostationary Earth orbit, which is the most important market for us, and up to exploration to the moon via Artemis program mainly, and to Mars exploration. So, as far as we want to qualify for space, we have to define what is space and what is specific to space environment. This is a very harsh environment condition, which can be declined in extreme temperature, very cold and very hot, depending on where the part is exposed to solar or not. Thermal cycling, because during the Earth round, it can go to sun side up to a shadow side, which lead to a cold and hot temperature every time during the life of the satellite. The outgassing is a problem that we have to face, not only for the material, but for the redeposition to other part of the satellite. Radiation resistance, because it's a huge problem in orbit, and vibration at launch, which is the main problem for a mechanical engineer. And we will see that our part is mainly sized by the stiffness in order to decorrelate the different modes of the structure. And the thermal expansion, either for stability of the satellite himself and for the thermal load that it could induce between interfaces of different materials. Thus, it requires to have a specific product knowledge all over the life of the satellite. It can be declined in 3 main. One, we are obliged to have a material supply chain with an excellent quality, because, as you should know, it's not possible to repair in space, at least at present time. And it implies to have a very selective supply chain in order to ensure quality. It implies as well to control all the process parameters which induce a very restrictive qualification method, and it passes by a continuous process monitoring and the storage of quality control data. And at the end, for technical parts, we are obliged to work with optimized thermomechanical properties in our materials, and thus we have to work with a high quality database and huge in terms of element of this database. So just to come back to the problem of mass, why it is so important in space. I imagine you've got the solution. This is due to the launch, because then in orbit there's no load, or at least no load. So most of the work of a mechanical engineer consists in working on the, let's say, 8 to 10 minutes of launch of the satellite. When we want to quantify the implication of such a mass during launch, we are used to apply a ratio of 15 kilo-euros per kilo. It depends on the launcher, on the position of the satellite on the launcher, and the mission itself. You can imagine that when you've got a satellite with many tons, it implies a lot of money. That's why we always are working on mass saving in satellite design. This is not the only thing, because now that launcher capacities are increased, it is possible to optimize the cost. Indeed, when you've got a mass saving, you can launch many satellites in only one launch, for example, when the launcher is able to. The other point is what we call snowball effects of mass generates mass. Because you can imagine that a Navy satellite needs more propulsion and more system to control altitude, so that it increases mass. In the same way, the mass induces more load at launch because of the weight, and so that the structure needs more reinforcement. So that's a very bad loop, because the mass induces mass. That could be synthesis in a small mass saving for structures and platform. It allows a significant increase of payload capacity, obviously at isomass launched. So now that we have take a picture of the mass problem, how to reduce this? Most of you know that the one way is to optimize the structure. That's the case for the sandwich design, for example, where the core is very light, keeping the flexural stiffness. Or the autopolycal optimization for metallic parts, for example. That is the case in many parts. The other way is to optimize the material properties. Often we choose high specific stiffness for material, and carbon is one of these examples for CFRP, for example, to reduce this mass. We have these two solutions, and now I will let David present his solution, which is
GRAM.
Which is GRAM, which is a common solution between a structural optimization and a material optimization. You will see it's very promising.
Yes. Thank you, Gilles. Concerning GRAM, is more GRADEL robotic additive manufacturing, which we developed in-house. And I will present you the advantage and disadvantage of such machine. Like it is mainly a robot, which is the impregnation head and the way of filaments and to wind and impregnation is everything in the head of the robot. We use industrial robots, and this gives us the advantage that we can use different materials. We have no sizes limit. For us, it's more difficult to make small parts than the bigger parts, and we can make complex, high-resistant shapes. Concerning the materials, we already tested carbon fibers, natural fibers, basalt fiber, glass fibers, and we can test many other fibers and resins. It means that if today you have resins, you have fibers, we can calibrate your material to be used in gram. Here is a small pictures of the gram winding, and as I was saying, no size limitation. It will be more your limitation of the facility and also the limitation of your oven if you need to make a curing on your resins. Gram, the advantage is that we have everything mounted on the robotic head, and this robotic head can be uncoupled and coupled. You have no loss of time, production time, and you can always keep your production running. Then it's possible to make 3D geometries. You can also adapt and make assembly of current parts which you are screwing and putting threads. You can make it at once. You will reduce the sub-assemblies which will give you more time. Complex, high-resistant shapes. We made, for example, a part which has 188 grams, and we reached 9.3 tons. And also for people who think that compression, it will not hold, here it's an example, 230 grams, and we put it with all our courage on top of the balance, and we have 103 kilos. Then I show you some parts which is made. You can also make intelligent, a functional part, which can avoid stress concentrations. It can dilate it according to your pressure in a tube, for example. You can combine also. You can equip some materials which you don't have currently. It has different applications. Concerning the homogeneity and the repeatability thermomechanical properties, we qualified our impregnation system with LIST, which is the Luxembourg Institute for Science and Technology. And we made a lot of tests and impregnation tests. We checked all the roving in different meters, and we reached really good quality of impregnation. This impregnation, currently, we are able to calibrate it by 60-40 or 50-50. Then we have also, we made in some test specimens, we cut different areas to see if the porosity is kept. We analyzed under temperature, in ambient, in negative temperature, and high temperature. And we have really a constant, like a good repeatability and continuous results. Then I will let you continue.
Okay, so let's go to the demonstrator. It has been developed in the frame of an ESA program, so with GRADEL and the LIST. And the objective for us was to design a new part. So we have chosen a part, it's a little bit small, but which is a TMTC antenna support. TMTC for telemeasurement, telecontrol. It allows to ensure the communication between Earth and the satellite. That's not part of the mission, of telecommunication mission, but it's a way to communicate with the satellite. So it's a quite critical part, because otherwise you can lose the mission if you lose the antenna communication. In the history, we had this support made of complex assembly, let's say, with panel composite, brackets, and so on, which were bonded, screwed, and it has a significant mass, let's say. This is the reference for us in order to save mass in implementing new technology. one simple optimization was made by a simple machining of a metallic part. This has been done, and it allows us to save about 30% in mass. It's quite good, but it's not sufficient for us. So in the last decade, we worked on the topological optimization, taking benefit of the additive manufacturing with metallic parts. And you can see in the middle that we obtain 40% of mass saving compared to the reference. We tried as well to include lattice in such a support, but at the end, we have on the right of the table, we have the same optimization of mass than a standard topological optimization. Then we had the proposal of the ESA and GRADEL to implement the GRAM system. And the study showed that we obtain a mass saving of 70%. This is very important. And now that's the most mass saving that we can have on this kind of structure. I just wanted to show you the drawbacks and the advantages. And the only drawbacks that we found for the GRAM technology is that it is not yet qualified. So we are qualifying the technology now, so that at the end we will have the lightest structure that can be able to ensure this kind of support. You should be aware that the mass of the structure is very, very low compared to the mass of the antenna that are above. So the structure is less than the equipment. I give you the floor for the description of the support.
Like all this, how we reach this structure is not only like we make all engineering inside of house. We take we take like the input from the customer, and I will let you go through the process, and you will see that we don't reach this. It's not so easy, because we need really to make a development in-house, how to optimize your structure, reducing weight, and so at the end that you have a product which is unique and accepts your requirements. Like here we made a demonstrator on a seat. This seat was made in basalt. We started by engineering, seeing the different deformations. We made some calculations, simulations, and then we come with a specific structure. Here, important with the GRAM is, it is important for us to know all your load cases. Load cases, restraints if you have cables passing, and then after that you have a unique product. Also, our idea is also to sell our machines to the production, because we don't intend to make production in-house of big quantities. We will make small production, but our idea is to follow the customer in all the steps so that he will be a production line capable to use our robots to produce. And with this seat, we reached to show that we can also use natural fibers. We have still a lot of development to make in this direction, but natural fibers is also a good solution to avoid carbon, or to substitute in a way which is acceptable. And with that, we thank you to be present. And if you want to have more information or see the products, don't hesitate to visit us in the Luxembourg pavilion. We are at Hall 5, stand E58. And for this, thank you very much. Any question? Yes?
Thank you for the presentation. I just want to ask, in terms of the optimization, did you just use the FEA simulation to get the topology structure?
Yes, we use the topology optimization to have a visual. We have a visual, but we cannot substitute the engineer which is behind. We use the optimization to see where the work and the flow of the forces are going, and then we take the decision, okay, it's realistic, or can we reinforce somewhere if we are not convinced what the computer is giving us.
Okay, thank you very much.
Another question? Okay, don't hesitate to visit us. Stand all 5 and stand E58. Thank you very much.
Brian gonna send you home a winner. But if you don't win tonight, man, kind of your fault. Ain't got no game. We're gonna set it up with some more. I don't know the rest of it. Wait a minute. I'm a prodigy. Watch this.